Buenos días a todos, vamos a dar inicio entonces a la sesión del día de hoy, ya la última de nuestra conferencia, y vamos a empezar con la ponencia magistral del doctor Ernesto Indacochea. Él, al igual que el doctor Unidos, es una de las personas que está con nosotros desde nuestra primera conferencia internacional, es decir, esta es su la cuarta presentación que ya hace acá en estos eventos. El doctor Indacochea ha realizado estudios de maestría en la Universidad de Marquette, en física, y en el Colorado School of Mines en ingeniería metalúrgica, y obtuvo su PhD también en esta universidad en ingeniería metalúrgica. Sus intereses de investigación están enfocados en, por supuesto, técnicas de soldadura y unión de materiales, recubrimientos, modificación de la superficie de los materiales, corrosión, degradación y, en general, caracterización de materiales y análisis de falla. Él ha recibido numerosos premios, tanto a nivel nacional como internacional. En particular, es profesor honoris causa de esta universidad. Además, es editor de varias revistas muy conocidas en el campo de la ciencia, ingeniería y materiales, así como en el campo de la soldadura. En particular, además, tengo el honor de presentarlo. Él fue mi asesor de tesis durante mis estudios doctorales, y no solo agradecido por todas sus enseñanzas técnicas, sino más allá de eso, la calidad de persona que es, ¿no? Es un gusto para nosotros tenerlo aquí, y lo recibimos, por favor, con un fuerte aplauso.
Well, thank you very much. I guess I can hear myself, so you probably are also able to hear me. Francisco, thank you very much for your introduction. Those feelings are the same. I feel the same thing. Was as I mentioned to some of our friends in here, that it was a great pleasure, and also I learned very much during your tenure at UIC. Also gives me a great pleasure to come here to the Pontificia Universidad Católica del Perú. Anytime they get a chance to come here, I'll do it. And in particular, this time, I have to congratulate you guys on the job that you have done in this conference. It's not only the technical program, but also the hospitality, which is second to none. So again, thank you very much, and it is a real pleasure to be here. I already used some of my time, so you have to discount that, please, all right? Well, we're all in the family. And what I like, the title of my talk is Intelligent Welding, Instantaneous Monitoring of Weld Defects during welding using acoustic emission and non-contact ultrasonics. Before giving the presentation, I want to give credit to my co-authors on this paper. As you can see, there's a whole list of different people involved with this project. And first of all, I want to acknowledge Dr. Didan Ozevin, who is the PI in this particular project. Alessandra Basantes, she's my master's student from Ecuador. She will be finishing her master's degree at the end of this month, and a lot of her data is included in this paper. Lu Shang is a postdoc for Dr. Ozevin. Sybil Derable, he's a professor also. He is the one who was in charge of the machine learning that I will present some slides on that. Professor Didem Ozevin, she is the expert on NDE. The other students are Nasir Ahmed, who just recently got his PhD, and he's going for a postdoc at Arizona State University. And finally, that's me. I'm the one who is doing the presentation, and I hope I give justice to the work that all these people have done. This is a brief, it's an outline of my presentation. I first will give you a problem statement, then define the objectives of this research, a very brief introduction, and then go into the detail of the work and discussion, come up with a is that okay? It's okay, okay. All right. So as I mentioned, many times welding is one of the last steps in any manufacturing process. So if any weld defect, okay, is going to have a critical impact on the product, on the integrity of the product, and might result, okay, in the product being disposed, which makes it very, very expensive. On the other hand, also you have, do exist monitoring techniques as it comes to in welding. However, some of these techniques, might be expensive, and most are done post-weld, and which doing the post-weld inspection, that also adds to the cost of manufacturing. There's also a need for, and sometimes there's a need for extensive processing of the data after welding. At the same time, many times, if you use just one single NDE technique, that could be inadequate to detect all the defects. So, based on that, and this problem statement, the objectives of our research are, number one, is to use multi-sensors, okay, that integrated with a scanner to do some real-time, collection of the data during the welding activity. So this way we can monitor the welding activity as well as the weld quality. Because of the amount of data that we will be collecting, we're going to be using machine learning methods to process the data. Of course, the ultimate goal is to use this multiple sets of data that have been acquired using different sensors. In our case, we have acoustic emission, ultrasonics, and welding sensors. And what we're trying to do is to integrate all this data into a real-time signal characterization. As we know, there are several defects that you can see in a weld. So in our case, we are concentrating at 3 specific features or defects. Number one is burn through. The other one is penetration and porosity. Okay, and well, there are 2 methods that we are using in this investigation. Number one is the ultrasonic or UT test and the acoustic emission test. Some of you are already familiar, and who are ND inspectors, they're already familiar with this particular techniques. However, I just give you a very brief introduction to the UT testing, which, as we know, is you are propagating a high frequency ultrasonic wave through the material, and usually those pulses change in frequency, and they can have a range from 0.1 to 15 megahertz, and sometimes can be up to 50 megahertz. And that it depends on the type of defect that you're trying to characterize. And of course, the most popular technique is the pulse echo, all right? So basically, in the case of the pulse echo, as we know, you use a probe that is both a transmitter and a receiver. So in the case that you don't have any defect in your material, we know that we have, you get 2 particular peaks. Now, if in the case that you have, without a defect, then you have more peaks that are going to, come into this screen. So that is one of the ways that you pretty much are, going to detect some of the defects. Now, of course, the defects come in different sizes. So therefore, one of the parameters or that you have to do some kind of adjustment has to do, the frequency. In terms of thickness, usually, if people want to measure thickness, usually they use a frequency of, in the range of about 15 megahertz. Now, if for porosity, when you're talking about very small porosity, then you have to increase the frequency so you can decrease the wavelength, and be able to, detect those particular, the porosity. In the case of the acoustic emission, basically, there is no transmitter involved. pretty much there's some radiation or vibrations coming out of the material that you are going to analyze. These are elastic waves, okay, and that usually occurs as a result of some changes that are undergoing in your solid. And some of these changes are, of course, irreversible. And based on that is that you can detect some of these defects in your solid. For example, if you stress the material, okay, so what's going to happen? You're going to have some kind of short burst or emissions of this, radiation, acoustic, radiation. That is what is going to be detected by the receiver. So in the case of the acoustic emission, simply what we have a receiver that detects or that receives any of the energy being released by any particular change in the material, in the solid. And some of these changes are dynamic processes or involve changes in the actual structure of the material. Not to the point of a crystal structure, but a little larger than that. And that is usually, when using the acoustic emission, you try to evaluate the intensity or the rate of radiation of these emission sources. One of the particular things that happens in the case of the acoustic emission, you do more than anything a qualitative evaluation of the damage. There's no too much quantitative, it's just qualitative evaluation. So based on this brief introduction, what we wanted to do is take our welding torch and then try to introduce some sensors, okay, close to the torch, and also which involve not only acoustic emission but also the non-contact ultrasonics, so that we can detect any changes doing welding, all right, not only of the welding arc, but also of some of the changes that might be going as you are producing the weld. And what we're trying to do is, again, we want to correlate some of the changes that you have getting the signal, okay, that might be related to the arc, but also could be related to the some of the defects that are being introduced during the production of the weld. Now, what we're trying to do is we're trying to see what parameters we can control so we can detect some of those changes. And what we're basically changing is the current, the voltage and the travel speed. So which we know what we're doing is we're changing the heat input. So it's a change in the heat input and then taking a look to see some of the changes that occur in the weld, but also during the process of welding. So change any type of amount of changes in the arc. Now, in the case of the acoustic emission, you have different data recording modes. Primarily you have what's called the hit-driven data, okay, and the time-driven data. And in the case of the hit-driven data, pretty much what it does, it records some of the signals that are above this set threshold. But in our case, we are using this what's called the time-driven data. Okay, that it does, it records any acoustic emission signals in a given set of time, and usually this TDD data is independent of from the threshold. So, again, as I said, what we're trying to do here is we're trying to monitor the arc, or I should say the change that you have in your current, in your voltage, as and those are going to be producing some type of emissions. So we're trying to take a look at this induced acoustics signals coming from the arc, but also coming from the well. But of course, when we have, in the case of the coming from the arc, that might be able to tell you about the different type of metal transfers, for example. Okay, and in the case of the weld pool, the flow of the weld pool, and during the solidification of the weld, you might have some changes, of course, from the liquid to solid, but also some solid phase transformations. And at the end, of course, one of the things we want to look at is some of the weld defects. I'm talking about porosity or burn through that I say we are trying to look into that, in this particular investigation, and also look at when I say weld morphology, look at the penetration or look at the cross-sectional area of the weld. So this picture pretty much is a little bit crowded, but I just spent a couple minutes trying to identify the different sensors. Okay, so again, this is our torch. As you can see, it's obvious that we're using a gas tungsten welding process. Okay, and we use this power supply, Maxstar 350, which is a Miller power supply that they also were involved in the project. And I must say that in this project is not only just a university, but also several companies have been involved in this project in our discussions and sharing of the data. For example, Caterpillar, Miller, Electric, and other companies. But anyway, so one of the things we want to do is take a look at where we're going to be, what are the things we're going to be monitoring. So we had the current sensor. It was the sensor for take a look at the current. Also another one for the voltage, and a gas sensor. Okay, and all this data, okay, is being fed into the this particular data acquisition system, which also was given to us by Miller. So we're sharing that particular piece of equipment. The base metal that we have used in here, is A36, ASTM A36, about 4.8 millimeters. So why did we select the gas tungsten welding process? As a matter of fact, we wanted to go with MIG, but in conversations with Miller, one of the things they want us to take a look at is using the TIG, and also looking at burn through. And the reason why we changed it from MIG to TIG is because that is is the cleanest process, right? And involves the least number of variables. For example, we don't have to use a filler metal that you have doing gas metal welding, and so you might have the design slow down of the wire being fed. So we decided to go just with the automatic gas tungsten welding. Now, as I said, we're trying to monitor the welding variables and also see the impact of the welding variables and the penetration and burn through, because pretty much burn through is going to be very much dependent on the type of heat input, on the heat input that you use. Now, the next thing that we were to take into consideration was how are we going to introduce some porosity. So one of the things that we decided to do is try to go with change the gas. Not only we use pure argon, but also decided to go with argon combined with argon 2% oxygen, and then we vary those volumes in order to introduce more oxygen, with the hope that we will have some more porosity. Now, in terms of, as I said, I mentioned earlier, in terms of the sensors, excuse me, in terms of the sensors, we use we have to use this scanner. Okay. By the way, this scanner was also manufactured by one of our industrial partners. So there's an industrial partner that we have in this project too. And what we basically wanted to do is make sure that we were able to synchronize all these particular sensors, all the different sensors with the torch. So we have this, it would be the acoustic emission sensors, and the bottom, okay, is this would be the UT sensors, okay. And what happens in here, you can see that you have I have mentioned that we have non-contact ultrasonics, but you say, wait a minute, you have rolling transmitters, so you're really having contact. And I'll tell the story a little bit later, but basically this was the original figure. Both of them were sitting on this part of the scanner. Okay, they were in air, so that how was we were trying to obtain some of the data and use this NDE data acquisition system. We use a MATLAB 8.5 script to extract some of this information. Now, again, as I just mentioned to you, all right. So this another picture of the scanner, all right. And this particular set of welds was done at Miller. So we went to Miller lab to do some of the scanners. So we wanted to do some in our lab, but at the UIC, but also went to Miller to do some of the welds in there, because we wanted to come out is really an applied research, and our partners want to get some information from there too. So the main thing is, again, it is important to synchronize both the sensors, the operation of the sensors, as well as with the torch, so we are obtaining the real time data. Because I think I have this little video that it pretty much shows. Let me see if it works or not. Is it working or not? Is it working? Okay, here it doesn't show it. No, I don't think. I don't think. Well, let me see. Let me try it. Let me try it one more time. No, it's okay. It's just very brief. Okay, there it is. Sorry. Okay, so as I said, in this case, this was the second part of the project that we're working on. The first one was using the TIG.
Is wide, so I'm hoping that the arc cone kind of washes on the side.
Okay, so I say who's talking to me. So as a matter of fact, that's one of the technicians for Miller, who was helping us in doing in that particular well. Now, of course, this is in real time that we have the weld going on. So again, in this case, you say come on, you're not using the gas tanks that are welding. We did that in the university. This one is the MIG arc welding, which at this moment we're doing some analysis of this data, right? So again, what I want to do is just try to refresh some of the objectives that I have mentioned earlier. Okay, so like I said, what we're trying to do is use processing, all the information that we obtain during welding, and using some type of machine learning methods, right? So if we're going to do that, we need to identify clearly what are the defects that we're looking at. Okay, so again, or some of the features that we're looking at. So again, it's burn through, porosity, and weld penetration, right? And so any changes that we see in those, in the welding parameters are going to be correlated with some of the signals obtained using the UT or the acoustic emission. And that is going to be then correlated with the weld defect. Okay, so one of the first things we want to do is take a look at the burn through. Okay, and what happens is, what is burned through for one industry is okay for the other, for another industry. For example, somebody who is doing very thin materials, burn through is a real issue. But somebody who is using very thick materials, for example, Caterpillar, when we were talking with with the people from Miller, they're concerned with the burn through because they were looking at very thin sheets, 4 or 5 millimeters. But the Caterpillar said, what we thought was a burn through, said for us that's a good well, And like I said, I say it probably would be a good idea to tell you what we consider a burn through in this particular investigation. Okay, so there are two things. One is melt through, and the other one is burn through. Okay, and I just wanted to give an example. Okay, for example, in the case of the burn through, we have a complete joint penetration. So like you see right over here, so you can see some kind of oxide. So you might have some partial melting of the backside of the plate, but the weld is contained in the plate, by the plate. Now in here you have, in the case of the burn through, for us, we define this as a burn through, especially in the kind of the thin 5 millimeter, 4.8 millimeter plate. And so that's, for us, that was a burn through. And of course, if you have a big hole, that is very obvious that you're dealing with a burn through. Okay, now, and again, one of the need that is is tied up with the burn through is the excessive penetration. And you can see here, these are two of our welds showing where we have obvious burn through as a result of a hole being produced. And of course, one of the things that when we're doing the welds, you come up with some areas in which you might have a crater. Okay, so the crater is some type of hole being produced in there. However, that is more as a result of this solidification of a casting, for example, of ingot, which we know as pipe. Okay, so that is not had to do anything with burn through. So in our first part, what we wanted to do is take a look and change the parameters, more current as well as travel speed. Okay, so if you take a look at this table, and I said it looks very confusing, but let me just drive you through this table in here. So at first we held the travel speed constant. All we had done, we changed the current. You can see the current 160, 200, 250, and 300 amps, all right? And you can see here, this is the heat input. So we have a change in heat input, and then we try to do some assessment of the welds and looking at, partial penetration, intermediate, so the immediate penetration, and then full penetration. And for the highest heat input, you can see it will be the onset of burn through, burn through, in which we had some partial melting, but you have, again, the weld was contained. And the same thing was in this case, we used, we fixed the current and we changed the travel speed. As you can see, the travel speed is right here. We slowed down the travel speed, so this way we were increasing again the heat input. All right. So the next one, the only problem with the next, you can see that in there or not? I think I have the two things superimposing there. It wasn't supposed to be that. Let me see. Let me try to go. Okay, that looks better. Okay, this. No, that was correct. I'm sorry. I have to apologize for that. Now the other one has to do with the changes in the production of the burn through. Okay, in the case of the production of burn through, we use a low current and a high current. And again, the only things that we had done in here is change the travel speed, and that will produce very high heat inputs. And you can see then some of the complete, actually we have burn through with some melting of the back plate for this in the low, low currents. In the case of the high currents, we actually see some of the holes being formed. All right. So looking at first of all, we wanted to do the assessment metallographically, so we can then, based on that, check with the changes that we have in the signals from the NDE. So everybody knows this is pretty straightforward. You increase the heat input, you're going to have a larger penetration, okay, and of course you're going to have an increase in the weld area. In the next, again, one other thing we want to show here. So as we change, the travel, the heat input, we do not have burn through when you don't have. And this is the front part, part of the plate. You can see that when changing the heat input and the mass of weld being, produced, increases. On the back side of the plate, again, you don't have any burn through, so you don't have any excess metal, weld metal coming out of that. Okay, but now if we decided to go and take a look at compare the changes in the heat input, okay, and trying to classify the type of weld that we have. Okay, so this is a little crowded, this particular graph in here, but very quickly, in this set of welds in which we have changed, we hold the current constant and we have the, we change the travel speed, slow down the travel speed. You can see the increases in heat input, okay? And again, this represents a good well. So this is a good well, as we have said, for this particular case. And again, you don't see any, you see the well bead well form. On the back of the plate, you don't see any liquid coming through, okay? Now, if we go to this particular one, all right, we have in here the for the high for the high heat input. So you go to 300 TS7, all right, and this you have in this particular high heat inputs, you can see some depression in the well bead, and then this is the front of the well. On the back of the well, you can see some of the metal coming out, and we define that as a burn through. So again, in between these two heat inputs, okay, the lowest heat input and it would this one's in here is what we have. Indeed, we have some type of the onset of burn through. Now this. In the case of, let me go back to this one over here. This one over here. Okay, this two again. This two in here. We have the the burn through is, and this one is burn through. But in between, when we have the well contained, there will be partial penetration, full penetration, but the onset of burn through. Now, when you go to the very high heat inputs, okay, and right now what we're looking at is the currents, the high currents of 300 amps, and you can see the holes are really being formed, okay, and you have burn through. So now what we have done is try to characterize or to correlate the heat input with the production of a burn through. So again, low heat inputs are going to give you good well. In between is going to give you the onset of burn through, and then burn through is when you have a hole really form. All right. So this is again, this pretty much summarizes what I just have said. All right. So any type of heat inputs around this area, this range in here, okay, are going to give you some type of the onset of burn through. Any type of heat input below this one is going to give you a good well, and then you're going to have a burn through when you have this range of heat inputs. All right. So now, having correlated the welding parameters with the quality of the well metallographically, we decided to go and take a look at the NDE signals. First of all, we take a look at the acoustic emission signals. You can see that as you increase the heat input, as you increase the heat input, what you have also, you have an increase in the absolute energy of the acoustic emission. So pretty much what we shows in here that the increase in heat input is being correlated with some of the changes that are being measured by using the acoustic emission. What about now the possibility or the occurrence of burn through? All right. So again, in this area right over here, okay, you can see that if we go back to the previous graph in here, those slopes are pretty much linear. I just want to call to your attention. The slopes are pretty much linear as you increase the absolute energy of the acoustic emission. Now, if you look very closely on this one here, okay, there is some areas in here that shows pretty much in here is in between. So it could be straight, but it's trying to do some kind of curvatures that try to bend upwards. In this case, right over here, you can see there is a larger curvature in here, okay, and we would try to correlate that with this type of depression, okay. So what we can based on this analysis, we see that the acoustic emission curve shows this tendency, and that is telling us that you have some possible burn through. When it comes to in the case of the real burn through, in which you have the hole, you can see this curvature even increasing to much greater. This one in here, you might say, well, you don't have too much of a curvature in here. Well, the reason is the well was very short because we immediately got a hole, so you got a burn through. Okay, so that was with acoustic emission. The one now we went to go and take a look at a non-contact UT. And this was all set up. Everything was, our setup that we have in here, okay? And we're using a, portable dual, channel tablet UT, which is, it's both for a generator, signal generator, as well as data acquisition. And we were all set to do some of the, assessment or evaluate the changes in the well. And what happens is when we start the arc, okay, and the signal all of a sudden just was interfered, so the signal disappeared, so went to zero. So we tried several times and tried to do some isolation of the sensors, and still no luck. So we decided to do is do some changes. Instead of using the non-contact, use some type of rolling transmitter, as you can see right in here. Was the rolling transmitter that we adapted. So that would, that was coming after the well. So you came, and as a matter of fact, I showed that the figure before, in which you can see that the transmitter, the rolling transmitter, was always behind, behind the torch. We put some shielding also of one of the sensors that was, which was the sensor for the receiver. Okay, and put some rubber pads also to isolate electrically the scanner. And these are the results, okay, using the rolling transmitter. And again, this is done post-well. Remember, this follows the deposition of the well, so this was post-well. And you can see here, in this case, for this particular well, all right, in which there was no, pretty much, we didn't see any burn through. Your signal was pretty much straight. Okay. Now, when it came to the to the onset of burn through, as I mentioned to you, you can see here is some cavity, some depression in the well metal. Okay, and that shows here this drop in the case of the energy ratio. You can see here again, this one in here shows it doesn't look any burn through, and this is the back side of the well. Okay, no burn through that goes with the signal right over here. But now in this case we have pretty much the onset of burn through or burn through. You have this depression, and you can see this drop in the acoustic energy ratio. When it came to the real burn through at the higher heat inputs and the 300 amp wells, you can see that there was a big drop in the energy ratio, in both wells in which you had this drop in the energy ratio. And again, this correlates with what we had called the burn through, because you have also the hole being produced. So now you say, well, okay, is it possible for us to do some assess the penetration, use any penetration using the UT rolling transmitter? So I'll show you here these 4 wells in which using 4 different heat inputs. All right, and you can see that in these 2 wells, you can see they're almost this, the same penetration. And here you have full penetration in both wells, more so in this one here for the highest heat input compared to this one in C. So we looked at the UT, all right, and this first was done before welding, okay, and you can see these are the 4 coupons that we have used. And why do you do it before welding? Because we wanted to check to see if there are any changes in the thickness of the plate. Because even though when you're getting the plates, there might be some small changes. So you can see in this case here, all of them pretty much the same. You have pretty much the same signal that indicates probably the same thickness of plate. But however, this one there was a little drop, okay, which might be associated with some surface roughness too. All right. But now when we go here and take a look at the energy ratio or the UT signal, you can see when we compare with the plate before welding, there is a drop in energy, in the energy ratio. These two have the same type of very similar amount of energy ratio, and we have said those have the same penetration. This other one here which we have the highest penetration, you can see a very drop in terms of the energy signal of the UT signal. We explained that probably as you put your signal through the plate in the UT2 signal, there's some attenuation coming from the heterogeneity of the plate. Could be the microstructure, but in this case, we're using a weld metal, which is a cast structure. So as a result, then you will expect that to lower the energy ratios. Now, having obtained all the data, okay, we wanted to do some assessment, some processing of the data. And for that, we went ahead and used some type of machine learning algorithms, all right? So to do some pattern recognition, and initially collected approximately 20,000 data points, okay? And again, we used this algorithms in order to group the different, the amount of data points that we had collected. So again, the different weld conditions, we try to make it as a function of the heat input. Okay, so the features that we used for the pattern recognition, where one was the welding heat input, two, they were related to the acoustic emission. We had two sensors. One was a narrow bandwidth, and the other one was a wide band sensor. Also, there were two sensors in the case of the ultrasonic data. Okay, to use the energy ratio and and high frequency. So this pretty much summarizes what we call that would be the supervised learning. So again, the goal was to identify the input parameters, okay, from the sensors, okay, which in this case we have the heat input, all right, the average signal with the two sensors, and the energy ratio and peak frequency that that has also two characters, and that data was collected at about 0.1 a tenth of a second. In the case of the average signal level, was collected at 200ths of a second, and the energy ratio and peak frequency was collected in per length, per millimeter. As we discussed before, we needed to classify the different type of welds, that will contain the defects. So the classes of welds that we had, remember, it was a good weld, the intermediate, heat input, which was, better penetration, and then we have the high heat input or onset of burn through, and you have the burn through. So you have, in the case, 4 classes. Okay. So in the case of the data analysis, we identify 4, classes, welds. 70% of all the data collected, was, used for training of the algorithm of machine learning, and the other 30% was for testing. The data was normalized for machine learning between 1 to 100 range for all 5 for all 5 input features or parameters. These input features that we obtained from the sensors. So we used the models that have been used to assess the data, or to try to interpret the data that compares the UT, the acoustic emission, and the weld data. These were the 5 type of models: the gradient boosting, random forest, SVM, neural network, and logistic regression. And this pretty much tells you the accuracy, okay, which is about 0.93, 0.89, 0.99, so which was pretty reasonable. In terms of the average prediction time, you can see in some cases we go all the way to 1.4 milliseconds. So it was pretty fast. This one again is another way to present the data. Okay, this is using the confusion matrix, and for the gradient boosting, we'll take a look at the measure and the predicted, both in the case of the detailed results as well as the normalized results. In all cases, there was pretty good agreement between the measure and the predicted. The only problem was when it came to burn through. And as I mentioned to you, the burn through sometimes, is that is the transition that is difficult to make a good assessment on that. The same thing was using the logistic regression model. Gives us similar results again as far as the good, intermediate, and offset of welding, the onset of welding burn through. That is pretty much they was very close to each other in terms of the prediction as well as the measure. And the only problem was again with the burn through that. Again. Also, what we decided to do, remember that we have said we were testing the UT, but the UT is post-weld. The UT is not done at the same time. It comes after the weld has been, is being, solidifying. So, excuse me, we look at the acoustic emission and just weld data, pretty much to take a look at the actual real-time, welding, all right? So we took the, real-time, we took the two sensors from the average signal level, the current, the voltage, and the travel speed. So they gave us a total of 6, features, okay? And then you can see the correlation was pretty good. So you have pretty much good agreement between the measure as well as the predicted value, all right? So proceeded with the testing of the data, okay, and again of the testing of the machine learning algorithms, and you can see for the good well, in this case we know that we had good well, and what was the prediction? So for this input, you have this indicated that you have a good well. For as you increase the heat input, all right, you can see now that you have some type of a burn through, but there was no hole, so there was a large, some amount of metal on the back of the plate, and we repeat it again with a second well, all right, changing the heat input, okay, and again, in this case, we had, for the high heat input, and on the right-hand side here, you can see there was no hole being formed. However, there was some of the metal that accumulated on the back of the plate, which again, it could be either burn through or could be the onset of burn through, all right? We try to also see the possibility on doing the detection, doing welding of some defects. And again, during the welding, we noticed in this particular weld that there was a spike at this particular location, right? This using the absolute energy as well as the ASL, right? And we went ahead and tried to locate the location where the spike occur, and you can see some type of depression in here, okay? So what this tells us that it is possible to obtain or to detect surface discontinuity, during the welding because of this sudden burst in energy. When it came to do some, you say what happened to the porosity? One of the problems that we have with the porosity was the fact when we used the linear ultrasonics. Okay, we looked at these wells that were fabricated using different heat inputs, all right? So you increase the heat input. These 4 wells in here, okay, these three wells in here were fabricated using the same heat input. The only difference is we changed the amount of porosity, okay? So these 3 ones in here, S2, S3, and S4, were the ones, S1, S2, S3, and S4 are the ones that have, the same, we changed only, we had changed the heat input was the same, we changed the amount of argon, 2% oxygen that we had. When we used the linear, ultrasonic testing using a 5 kilohertz, you can see there was no correlation between the changes in heat input, all right, with a signal, the UT signal. The same thing and remember that in here, the heat input is the same. The only difference is that we have changed the porosity, so we have increased the amount of oxygen. We went with increased the frequency to 1 megahertz, okay? And again, you can see that there was some decrease in the energy ratio, as a matter of fact, because we have more dilution, or more attenuation of the wave, and you can see the drop in here, okay? So in a sense, when we go to higher, frequencies, it is possible to detect some changes in the penetration, okay? However, any changes in the case of porosity were not there, could not be detected. Using nonlinear ultrasonics, okay, with 500 kilohertz, so that would be high harmonics, okay, in between 500 and 100 megahertz. What happens in this case, you can see there was, using the high harmonics, you use this parameter, which is a beta parameter that was correlated with the heat input, and you can see that as you increase the heat input, you have also an increase in penetration, all right? Now, remember that I mentioned to you before that in these two cases, it was very difficult to detect any type of porosity. In this case, okay, it did. You can see they have the same heat input, however, you have some changes in terms of the beta parameter, which indicated that can also be detected using nonlinear ultrasonics. We can detect porosity. This leads me to the conclusion, and I'm sorry, I went a little over time. And first of all, we can see that non-contact UT cannot be used for real-time monitoring because the UT signal got pretty much blocked by the arc, by the magnetic field created by the arc. However, it is adaptable for in-situ monitoring, post-weld, using a dry couple rolling transmitter. A pattern recognition of burn-through damage with multiple data is being performed with encouraging results. A machine learning algorithm based on the acoustic emission, UT, and welding parameters to have a quantitative understanding of the weld at post-weld test is being developed. Initial results are promising. And last but not least, I have to acknowledge the people who give us the money so we can keep getting more money. And that's the University Industry Labs of the Digital Manufacturing and Design Innovation Institute. And of course, ITW Miller for providing the equipment and the weld acquisition equipment system. Thank you very much.
Muchísimas gracias, doctor Indacochea, por su excelente presentación. Lo invitamos a sentarse en la mesa para poder continuar con las sesiones.